Hi, I'm Mike Tochik, and let's talk about misunderstandings that relate to overvoltage protection. Here at Dairyland, we've heard so many of these that we decided to actually make them into a top 10. So, let's take a look. Number 10. We hear that safety grounding mats make great AC mitigation grounds. So, let's talk about grounding mats. Gradient control mats are meant to limit step and touch voltage. So the touch voltage that could occur between your two hands or between your hands and your feet when you're standing and touching a pipe. Or step voltage would be the voltage difference between your 2 feet if there was a voltage gradient in the earth and you weren't touching anything at all. So gradient control mats are meant to address AC faults and lightning conditions, and they will depending on the design. And they're installed typically around piping and test stations. You might see them on a right-of-way near power lines. And they're installed in the end with high resistivity fill, gravel, being put over the top of them. So here's a depiction of what this might look like. Here there's a touch voltage between this person's hands and the feet where they're standing on top of a mat installation with gravel on top of it. Or if a person wasn't even touching the pipe, there could still be a step voltage present, and the mat is attempting to address that. Now, the goal is to have that grounding mat limit the voltage gradient in the earth and limit the touch voltage. And after we apply a mat design, and that's not a discussion not here, but in another slide, we have limited the voltage, hopefully. And then to make that even more effective, one would add high resistivity fill on top of the mat, and that limits how much current could flow through a person, basically due to step voltage or touch voltage, and provides even better effects. Well, the high resistivity fill gives that a high resistance to earth, and if you have a high resistance to earth, you're not going to have much AC mitigation taking place. It's not that great of a ground. So, gradient control mats really can serve a useful purpose for step and touch voltage protection, which is really personnel protection. And AC mitigation designs rely on a low resistance ground to do the job of mitigation. But you don't get both in this same story. There are other AC mitigation grounds that are being used to perform those functions, and gradient control mats are being used for personnel protection. So, in the end, safety grounding mats don't make great AC mitigation grounds. Number 9. Conductor length doesn't matter. Well, let's talk about conductors. Any conduction path, whether it's a piece of pipe or a cable, it has an electrical property of inductance. And what that means is that the property of inductance will resist current changes. And if you attempt to change the current abruptly, you'll get a very large voltage difference present. And that voltage can be quite notable. Where this will matter the most is where you're dealing with a person that obviously can't withstand all that much voltage, or maybe an insulation system that can't sustain that voltage. That's a concern. So at insulated joints, we would have only 1/8 of an inch of insulation separating the 2 flange faces, or the coating, which is not that thick, or insulated fittings, which are rated for even lower voltage than insulated joints are. Those have to withstand voltage. If you can't withstand voltage, you would generate an arc. So here's an example of an insulated joint. We're attempting to protect it with a device and hook it up with wires. This is how this relates to our story about conductor length. So we have cable number 1 and cable number 2 connecting this protective device. It doesn't really even matter what the device is in our story. But there will be a voltage drop due to a fast rising waveform, which will interact with this inductance property we talked about. And as current flows in cable number 1 and 2, there will be a voltage drop generated in the lead itself, and also one across the product as it does its protection function, and in the second lead as well. So the total voltage across this flange face will be the voltage in the first cable, the second cable, and the drop across the product itself. And the voltage that relates to inductance is determined by the rate of change of current and also the inductance of that path. Well, the inductance comes from the cable and its length. The rate of change of current is really dealing with lightning, where it's a very fast rate of change. And we're going to plug some numbers in here, and you'll see a result that's pretty high. And that is a value that is in volts per foot, or volts per unit length. And that value might be higher than you'd expect. By the time you consider the total length involved with connecting a product, or connecting between two grounding systems, let's say, you could end up with substantially different voltages between those structures. Number 8. So back to ground mats. So all ground mats provide personnel protection, don't they? Well, let's look at the mat design. There are a couple different designs that are possible out there. They can be boiled down to really just two. Something made up of a single wire, such as a spiral arrangement or a zigzag pattern, but it's still just a single wire, or something involving a grid arrangement with intersecting wires. So on the left, we show that single wire arranged in a spiral, where somebody would bend or place wire in that spiral pattern. And on the right, let's show a grid arrangement where larger sheets of the grid material are bonded together to make this larger area of coverage. So back to our discussion about conductor length. If you have increased conductor length, you're going to have higher inductance and you're going to have a higher voltage. And under AC fault conditions, the inductance isn't that high as it appears to an AC signal. But to a lightning waveform, that inductance is very substantial and it will result in a very large voltage. So we're mainly concerned with grounding mats with lightning effects, not as much AC fault effects. If it can handle lightning conditions, it will automatically handle fault conditions for overvoltage purposes. So here's the voltage gradient across the mats that we're concerned about. So from the center, radiating outward, we would look at the single wire mat and look at its voltage gradient, or we would look at a grid mat and see its voltage gradient. So that's what we're going to do next in a table. So there's a lot of data here, but on the left, we have a single wire mat of some design. Let's say it's a spiral mat. And on the right table, we'll have the grid mat. And then for both of these, for the same distance away from the center, in this case we're giving this as a radial distance. So imagine a 12-inch diameter pipe. So the start of that pipe is at a radius of 6 inches. So our table starts at 6 inches as well. And you'll note that the voltages are all 0 when you are 0 inches from the pipe. And then outwards, every 12 inches, let's show the calculation for where the voltage would be for a single wire mat on the left and a grid mat on the right. So you'll see that at the 18-inch mark, which is 12 inches out from the pipe edge, the single wire mat has a 48. Well, you'll see an entry in the table that says 48. You'll notice it's also in kV. And you'll see that that value gets higher as you go further out in the mat. The touch voltage goes higher. You'll also notice that the step voltage, which is the volts per foot, is also increased as well. You'll note again, these are all values in thousands of volts, or kV. On the right, let's look at the grid mat. Same distances away from the pipe wall, and notice that the touch voltage is increasing as you go out in radius. But notice that the step voltage is decreasing. Well, what's at work here is the decreased inductance of all these intersecting grid wires from a grid mat design means that it has lower and lower inductance as you get further away from the pipe. There's more area that you're standing over, you could say, or more area to take current. But on a single wire mat, there's a longer and longer wire, and there's greater and greater voltage per turn until it gets unreasonably high at the edges. Note back on the grid mat, these values in this table are all in volts. And in the single wire system, they're in kilovolts. So roughly, there's 1,000 to 1 voltage difference between a grid mat design and a single wire design, where the grid mat has a much, much lower and safer voltage across it. It also has the benefit of having a lower and lower voltage as you get towards the edge as compared to a single wire system where there's a higher voltage as you approach the edge of the mat. So they really aren't all the same. Number 7. So all this talk about conductor length clearly shows that conductor length must always matter, right? Well, if you have to withstand voltage and you don't want insulation to break down, that does matter. We have to think about conductor length, and there's applications where that becomes critical, such as insulated joints, insulated fittings. They can only withstand so much voltage before there's an arc. And certainly, we want to make sure that we bond different structures together, different piping systems, grounding mats, fences, things like that. And in those examples, we usually can always control conductor length, and it provides a benefit to us. However, there are some applications where you really can't control the conductor length. And so now you have to think about whether that is a substantial reduction in safety or not. Let's look at an AC mitigation system. There will be a mitigation wire, let's say, that follows a pipeline, and a decoupler or protective product that does mitigation has to be mounted at ground level or above ground and have wires that connect down to the pipe and down to the mitigation wire. Well, you can't really shorten that conductor length much in order to connect between those two structures. Or think about a decoupler that's used to provide CP isolation in an electrical grounding system, which is another application that Dairyland tackles, in that we aren't talking about it in depth here, but products may be used in this manner if they're certified. If a decoupler is placed in an electrical grounding system, that ground runs from an electric panel out to a load, such as a motor-operated valve in a pipeline or on a tank, something with CP. Well, that grounding conductor that runs from the panel to the tank or the motor can't be shortened, and it can't really be altered. It runs between points A and B. So what do you do about conductor length? The answer is you do nothing about conductor length. You can't shorten it. The grounding conductor is needed for safety, and you can't really shorten it practically. There are more important things we're actually chasing in those applications, and that would be we're handling AC fault current conditions. We might be handling lightning conditions. But the main thing is we're handling AC faults in some of those, and there's no practical way to shorten conductor length. Number 6. So some say that lightning is a lot like DC. I've heard that one quite a bit. Some might even say lightning is like a fault. Well, lightning is not like either of those two. The reason is it produces very different effects on a pipeline or on a system or on a person that is subject to that. And the reason is the lightning waveform is rather unique. It has specific characteristics that make it quite different than AC or DC. Here's a representation of a lightning waveform. It has a very fast rise time up to some peak value and then a decay back down to a low level. And the waveform can have different shapes, but there are some industry standards that relate to this. But in general, one could conclude it does have a very fast rise time. It generally has a fairly high current magnitude. And those things are different than an AC fault. So what you can do about this is, back to our conductor length discussion, is you can keep conductors short in order to deal with and limit the overvoltage due to lightning. The other thing is to make sure that structures that are near each other are referenced to each other in order to keep them near the same voltage. You would not want to leave something ungrounded or unreferenced to another object, or one could rise in voltage compared to the other. Interestingly, one thing that's unique to lightning is you do not have to have a very large conductor in order to handle that current. We've done lightning current lab testing, and we've put 100,000 amps of lightning surge current through a very small conductor. I think it was a number 8 conductor, quite small. Certainly even a number 6 could handle any reasonable lightning surge. The reason it can do that is the lightning event is over so quickly. So even though it's a very dramatic effect and the lightning current is very high, the duration is very short. Number 5. So monolithic joints must not need protection. After all, they're pretty fantastic. Well, they are a factory assembled kit. You weld this into the pipeline. It has very specific, consistent design and construction. And they can withstand much higher voltage than some type of field assembled flange joint. But that voltage withstand is not unlimited. Even that kind of a device needs overvoltage protection. If you don't apply overvoltage protection, what somebody might be thinking of doing is trying to permanently, totally isolate one structure from another under all conditions and never protecting it. Well, eventually there will be a voltage high enough to arc across the monolithic joint, and monolithic joints can suffer failures, but the arc will be initiated at a much higher voltage than, say, a field assembled kit. In the end, it's all the same. It can fail if it has a lack of overvoltage protection. Number 4. People might say to me, I only want to mitigate the AC, but I don't have any risk of faults. Well, that's just not possible. Let me explain why. If AC is induced from overhead power lines onto a pipeline, the reason we get that effect is because there's current flow on the power line. It causes a magnetic field to surround that current flow, and that induces a current and voltage on the pipe as it interacts with a steel pipe specifically. So there's a lot of factors that go into whether you will have a high level of induction on your pipe or a low level. Things like soil resistivity, the quality of the coating, the distance from the conductors, all kinds of things like that. But if you can have a steady state AC effect that you can measure, you can feel, then there's other things that come with that package. You're experiencing induction on the pipe, and I want to relate that to relate the steady state conditions also to fault conditions. So the steady state is an AC signal. Well, an AC fault is an AC signal as well. And the steady state is just a small version of a fault condition. Well, if an AC fault is just a higher amplitude version of the steady state induction, the same phenomena is really at work. Under normal conditions, you get steady state, moderate or low level induction, but it's still the magnetic induction producing this effect. If there's a fault, you get a much bigger version of this very same effect. Yes, faults are not that common, but when they do happen, they have enough potential to cause an arc and damage coatings and steel. So you absolutely can have or will have elevated voltages under fault conditions when you may be only out on the site and measuring lower level steady state conditions. Number 3. Someone might claim, I want to totally isolate one structure from another. The idea is, I don't want this stuff on one side, bad electrical effects, from getting onto this other equipment or this other side. So I'm going to permanently isolate this section of piping from that section, or this facility from the other facility. Well, that might be the idea, but that's not how electrical principles work. The problem is you now can have elevated voltage on that isolated structure that has no reference to ground. There's no ability to limit the voltage. So clearly you could have a shock hazard, you could cause an arc, could cause ignition of product. So there has to be a protection method applied to isolate a structure for CP, and that's how we use insulated joints of various kinds and coatings, so now that you can have a manageable CP system. However, you must apply overvoltage protection or one structure is permanently unreferenced to the other, both under steady state conditions but also under fault or lightning conditions. And if you apply overvoltage protection properly, you will limit voltage and you will allow current to flow, and it might flow onto this other structure that concerns you. However, current flow is not necessarily a problem at all. It's a matter of how that current got on the structure and how it got off the structure. And there will be no hazard to the structure as long as the exit for current is through a proper overvoltage protection device and perhaps a grounding system. One has to also think about performing overvoltage protection, say on a section of piping that has AC induction on it, but then not forgetting that that pipeline might leave the right-of-way, go somewhere else, but might have a discharge of current at a location near a power substation. So one has to think about protection there as well. But what we don't want to do is to say, I want permanent isolation of these structures with no overvoltage protection. Number 2. Decouplers are one-way devices, as if they would conduct in one direction but not in the other. They would let fault current or lightning get off of my pipe but never let it get on my pipe. Well, that's not true either. Decouplers are solid-state devices that provide overvoltage protection, and they can perform AC mitigation, very, very common applications for these devices. These devices do have a threshold in each polarity, the positive and the negative, and within a band, they will block DC current flow, cathodic protection current. And outside that band, it will attempt to clamp the voltage and allow all current to flow. It's performing its protection function. And at the same time, decouplers can conduct AC, and the example would be for AC mitigation on a pipeline that's under a power line. So graphically, here's the threshold of a decoupler with a pretty typical industry value of -3 volts to +1 volt. There are other decouplers that block from -2 volts to +2 volts. But what you can see in this graph is inside of that band, the device is in its normal mode. It's blocking CP current, DC current. But upon reaching the voltage difference between the terminals of -3 volts in one direction or +1 volt in the other direction, that the device would essentially turn on, clamp the voltage at that threshold, and allow all current to flow. So what this clearly shows is the device can conduct in both directions, both polarities. It doesn't only conduct in one polarity. If devices like decouplers were only one-way devices, then they would conduct in one direction, and they'd have to withstand the full reverse voltage in the opposite polarity and then never conduct. Well, if that's true, then the voltage in that polarity would be allowed to go up to any level. Well, at some point, the voltage would cause the product to fail in that polarity. There'd be no control or limit on that voltage. It's clearly an unacceptable situation. So while someone might dream about devices only letting current get off my pipe and never get on my pipe, it really doesn't work that way. You want overvoltage protection in both polarities for your benefit, and not allow the voltage in the what we'll call reverse polarity to reach unacceptable levels. And number 1, grounds can affect cathodic protection, and there are some grounds that might be tempting to remove, and there are some that you can't remove. We want to address that. If there's AC powered equipment in a facility, it will have a grounding conductor for safety purposes. The purpose of a grounding conductor that goes out with the phase and the neutral, whatever the arrangement is it's supposed to handle fault current if there's a winding fault in the motor or cables short out and the insulation fails. It will handle fault current. If that happens, then a breaker back in the panel will sense the fault current, interrupt that current, and clear the fault. And that can happen in just fractions of a second. But if you didn't have that ground, the fault clearing would be affected. In fact, the fault clearing might not even happen. So here's a depiction. On the left, we have some kind of service panel, electrical panel, that's supplying power out to, let's say, a motor-operated valve in a pipeline, or perhaps it's a pump on a tank. Something that has cathodic protection. And we also see a grounding conductor shown here, because that's required per the electrical codes to ground that motor. And if the motor's touching the cathodically protected pipe or tank, then your CP is bonded back to the panel ground and on to the rest of the world because it's bonded through to the utility as well. So this is the grounding conductor that causes the problem. You might be tempted to do something with that grounding conductor. There are some things you can do and some things you can't do. Please don't do this. If you were to sever the grounding conductor and just have a local ground rod and think to yourself, I can cathodically protect this one local driven ground rod, but then that's all I have to protect. I won't be bonded to the rest of a facility or to the power utility. It might be nice in concept, but it doesn't provide adequate protection in practice. What can happen is there's not enough fault current that might flow into the earth with no hardwired return path back to the panel and the breaker. The breaker may not sense the fault and may not clear, and a fault can sit there and persist. This depiction here would never meet an electrical code and should never be used. So there are CP problems where you can remove an inadvertent bond or a piece of conduit that causes a problem, some type of inadvertent short. But if it's an electrical system grounding conductor, you do not want to remove that ground. The way you deal with a grounding conductor that causes CP problems is to use a certified decoupler in series in that ground, and it meets the National Electrical Code. It would be rated for fault current. It would block CP current under normal conditions, and then it would switch to a shorted mode if there was ever a fault. And then when the event is over, the device just goes back to the DC blocking mode again. So there are acceptable ways to fix problem shorts or grounds, but you don't want to sever an electrical system ground that's used for protection. So that's our run through of some of the top things we've heard that were misapplied for overvoltage protection. And if there's more questions that you have, feel free to contact us, and I've listed my contact information here. We have application engineers that deal with these kinds of issues every day, and we're glad to assist.